Topic. First of all, hello to everyone. It's good to be here. It's my first time on Sicily and also in Syracuse or also in Ortiga. And I'm from the Technion, Israel Institute of Technology. My name is Pavel Galich, and I'm head of the lab wave mechanics on wave mechanics and meta materials. And today I will be talking about phononic crystals. So, and in a bit I will explain what phononic crystals are and why do we care about them. I also would like to acknowledge my graduate student Ilya Nadezhda, who did most of this work, and also my collaborator, Professor Ned Thomas from Texas A&M University, with whom I also did my postdoc at Rice University. And of course, I would like to thank the organizers for organizing this conference. The phononic crystal. So the most primitive example of the phononic crystal is the simple laminate. It's also sometimes called 1D crystal. And imagine if we vibrate the left side of it, so then on the right side, the vibration of certain frequencies will be able to propagate. But if we change the thickness of the layers, for example, or the period of our laminate, so we can block the certain frequencies, meaning that we will have the band gaps of forbidden frequency regions. The beauty of the phononic crystals is that they are scalable, and maybe I'll stand here, I think it will be easier. Yeah, now you can see all of you. So they are scalable, and if we are talking about the cell size or period of our periodic structure on the scale of the human height or meters, then we are talking about the seismic barriers. If we are on the centimeter scales, then we are talking about audible frequencies, and this is just a piece of art. Just two physicists were passing through it, and they noticed that this is just a steel area of steel cylinders, and it's periodic. And they actually did measurement and published this in Nature, that it actually filters the certain audible frequencies. Then, if we make our cell size smaller, we can go to the gigahertz or even terahertz regime, and where there we can speak about the thermal insulation. Of course, there everything gets everything a bit more complex. And today I will focus on the ultrasound range, because we can easily do experiments and also the fabrication of the crystals at this scale. Again, already mentioned that there are already proposals, and now actually phononic crystals got significant attention in seismology. So people try to use them as a seismic for the seismic shielding. So here you can see, for example, building and the seismic wave propagating. So, and if you don't have the phononic crystal next to it, here maybe you can barely see it, but there are phononic crystals embedded into the soil. So if you have phononic crystal, then your building is not shaking, right? So, and if you don't have it, here you have like significant displacements within the building. So the phononic crystals, they can either attenuate or simply reflect the seismic waves. Then they also can be used for the wave guiding, energy harvesting, and more recently, you see it's 2023, it's very recent paper, US Air Force got interested into the use of the phononic crystal for the control of the transition from laminar to turbulent flow in the boundary layer in hypersonic regimes. Okay, and I'm myself from aerospace engineering, so I'm very interested in this kind of applications. And in this paper, they propose very simple phononic crystal. As you can see, this is just a 1D phononic crystal, but I'm trying to develop more advanced and like 2D phononic crystals, and to see the connection between the symmetry of the structure and the band gaps or the band structures. And before talking about phononic crystals, I must introduce the Brillouin zone for those of you who are not familiar, because you will see it like a lot in today's talk. For example, if we have a simple cubic lattice, so I guess everyone is familiar with the primitive cell or unit cell when we have just connect like two lattices and we get our square lattice, right? But if we go to the reciprocal space, which is the Fourier transform of the Bravais lattice group or real space, then there we can define also the primitive cell, which we call the Brillouin zone in the similar fashion. This Brillouin zone can be further reduced if our structure is symmetric. Okay, and so this is a shaded triangle. It's called irreducible Brillouin zone, and these gamma, x, and m points are has certain point symmetry groups. So 4 stands for the fourfold rotation, m for the mirrors, 2 for the fourfold rotation, and this is how they denote it. Okay, and depending on the symmetry group, we can of our periodic structure. We can immediately define the irreducible Brillouin zone, and then we need to solve the wave problem, like eigenvalue problem, only for this range of the wave vectors in the K space in order to claim the band gaps. Okay, a bit more about the symmetry groups for those of you who are not familiar. Maybe if you have, do we have someone from crystallography here or metallurgy? No. So in crystallography, in general, in 3D, we can describe any periodic structure with the 230 space groups. Okay. In 2D, we can describe any periodic pattern, like I stress this, any, just with the 17 plane symmetry groups. So the number of choices of different patterns, here you can see one example, and later you will see more. It's infinite, right? So we are limited only by our imagination, but beautifully that we can describe any of these patterns just with the 17 plane groups. And 4 of these plane groups are non-symmetric. Non-symmetric meaning that they have the glide symmetry operation. So when I walk, so the line between my legs, this is the glide. So I have reflection and then translation half a period, as you can see here. And the non-symmetric symmetry group, it has been shown, has increased band gap size, where so-called phenomenon as the band sticking. Okay, but in this talk, I would like to focus more on the symmetry groups with the square Bravais lattices. Okay, so in here you can see the 3 different patterns, like Egyptian tomb selling, Assyrian ornamental painting, Chinese painted porcelain, and they belong to the different symmetry groups. So the first one, this is the P4 group. Meaning P stands for the primitive and square Bravais lattice, and the 4 means that it has 4-fold rotations. Okay, so this square means that if I rotate my against this axis my structure 90 degrees, it will be the same. Okay, so the P4 has only 4-fold rotations. P4MM has 4-fold and also mirrors, and P4GM also has glides. Right. And the shaded area, this is the asymmetric cell, meaning that if I put anything here, it will be replicated. Okay. So So just a bit of theory, and you probably have noticed already that all of these symmetry groups with square Bravais lattices, they have also fourfold rotations. And these are the only 3 groups out of 17 which has fourfold rotations. And we decided to explore how this symmetry groups, like, will be there any difference in the band structure if we change the symmetry group. But basically, mechanically speaking, we have the same square resonator, just we make different groups from them. Okay? Because before, it has been reported that the P4GM, the non-symmetric plane group, superior than other symmetry groups, and then the chances of finding the bigger band gaps are higher. So we decided to check if it's indeed true. And here we propose very simple structure. This is just a square grid, or which is made just from the thin connectors, we call it. And then we put just a solid square or resonator in every second node. Then we rotate it 45 degrees, and then we rotate it in different angles. And if we rotate each layer in the same direction, we will obtain the P4 group. If we rotate each layer in different directions, like clockwise and counterclockwise, that we will get the P4GM group. And know that for the P4GM group, the primitive cell is larger. Okay, and when we want to do the band gap calculation, we must define the Floquet periodicity conditions on the boundaries of the primitive cell. Otherwise, if we take a supercell, which is sometimes done in literature, we will induce artificial periodicity, and hence our band structure will not reflect the actual reality. So to model these phononic crystals, to model this family of the 2D phononic crystals with the Bravais lattice or fourfold rotations, we use the classic Bloch-Floquet Bloch-Floquet approach. So meaning that we apply Bloch-Floquet periodicity conditions at the boundaries of our cell. Then we approximate that not as a solid air, this crystal, but solid void, because the acoustic impedance contrast between the air and solid is like 3 orders of magnitude difference. That's why we safely can assume that this is just a void and can neglect any air structure interactions. So then, and on the free boundary, we apply just the free boundary conditions, so no tractions. Okay, and so this is to calculate the band structure for this irreducible Brillouin zone that I showed to you. So basically scan for all the k vectors. And then we also do the transmission loss when we shake left side and measure displacement on the right side, either longitudinally or transversely. So we can mimic the pressure wave or shear wave excitation. And also later I will show you our experimental setup. And in this experimental setup, we use 2 transducers, meaning that we pick up signal immediately. So that's why we also lag the reflection on the right boundary. And if we do all these calculations, we, for example, and compare the P4GM phononic crystals with the P4MM, which is just square array of circular openings, then immediately we can see that this P4GM crystal beats the classic P4MM immediately. And for those of you who attended the previous conference in Algero, I already showed that, and there we claim that P4GM is the best symmetry group that you can use. But why does it happen? to answer this question, we need to look into the real spectra for the imaginary wave vectors. Okay, and that's actually I got this tip also from the previous conference from Algero, but I don't see. I don't know if these people are here now. I'm not sure, from Vibroacoustics. So I want to thank them. And so then, by looking into the real spectra for imaginary wave vectors, we discovered that in single-phase phononic crystals, bandgaps occur due to the Bragg scattering and local resonance effects. And the Bragg scattering results from the destructive interference on the periodic impedance contrast, governed by the Bragg condition. And the local resonance typically occurs on this scattering on the local resonators. And this is usually happens on the lower frequencies, and here you can see example of the vibrating local resonators or vibrating connectors. And these frequencies of the vibration will be different. Consequently, we will have different band gaps. Now, finally, let's look at the band structure for the most primitive crystal. So when we have just a square grid or just in connectors, then both the black, this is the real spectra for the real wave vectors, meaning that these are the allowed modes. Okay, and the red, this is the real spectra for the imaginary wave vectors. So if we don't have the local resonator for the square grid, we don't have any band gaps. Okay, if we introduce even a small resonator in the every like second node, then we will start to see the small band gaps. If increase the size, the band gap size will increase. Right? But let's look closer into the band structure, so then you can understand better what the meaning of, because these are the black, these are the allowed modes. And the lower slope here at gamma x, this is the long waves. So here the wave number is close to 0, meaning the wavelength is very large, and the wave doesn't actually see the structure. So this the periodic structure we have. So this band will be the shear wave band or transverse wave band, and this is the CS velocity, which is the square root of the shear modulus over the density of your solid, and the CP, this is the square root of the Young modulus over the density. So these are the slopes, and this is the allowed or propagating modes. But for if we look at the real spectra for imaginary wave numbers in this direction, so when we have the band gap, so we will have this large distance for imaginary k till we get the real eigenvalue. And if we plug in the imaginary wave number to the plane wave expression, then we will see that actually the value of this k will tell us how quickly and how strongly the wave will attenuate. And so just by measuring this k, we can say either the band gap attenuate better or not. So this one, low one, is the resonance band gap, and the top one, where k is very large, and they also meet here at the middle. You have kind of like a hat here. So then this is the marker of the Bragg band gap. So this is how we can understand how good our band gap is. I mean, meaning its attenuation performance, and also either it's a type, is it a Bragg or it's a resonance band gap. Okay. So then we decided actually to confirm our findings, and either indeed we can predict how well the band gap will attenuate. And for that we built very simple ultrasonic setup. So we put it on the vibration isolation platform, and then we took the two ultrasonic transducers, P-wave transducers, and S-wave transducers. So before that, we could measure the wave speed for our solid, which is the Formclear V4 printed on the Formlabs 3D printer, and just measure the transmission loss. So everything very simple. Here just, so these crystals are the size like 3 centimeters over 3 centimeters cube. So the lattice side is the 8 millimeters. Here, like just more printed examples. And so, and now let's see at the actual transmission loss for this P4MM crystal. Okay, so here the first one is for the P wave, the second one for the S wave, and for the different resonator sizes. So we can see the good correlation, because the red area defines the band gap for the larger resonator. So here we can see this transmission loss peak, and also we see it for the shear wave. However, here we have for the small resonator we have something that is like very high attenuation, up to -80, but it's not within the band gap. So why does it happen? If we look close at the band structure, we will see that this is actually so-called single mode band gap, meaning that even though we have allowed modes here, but these are the shear wave modes. So these arrows denote the shear wave polarization here. So that's why we had the spike, meaning that it still agrees with the band structure calculation. Then, if we change the resonator size, we will see that for the alpha of 0, it will monotonically increase with the resonator size. So that's why like nothing that it's not that interesting, kind of expected. But if we rotate our resonator for the 45 degrees, and then also keep increasing the resonator LR, at some point we will reach the peak, and then the band gap size will decrease. So why does it happen, right? So it's intuitive, because we have larger resonators, so we would like, so we expect the larger band gaps, but indeed no, it shrinks significantly. And this happens because the connectors, they become very narrow, and when they are very narrow, so the resonator it's more difficult for resonator to resonate, and also its frequency increases, and that's why we have shrinking of the band gap. And here also, if we look at the imaginary part, we will see the strong coupling of the resonance and Bragg band gap, because it's not here, the imaginary K is very very far. Then let's look at the P4GM phononic crystal for the different when alpha is 30 degrees. How much time do I have? Like more? Okay. When the alpha is 30 degrees, the resonator size is 4 millimeters, meaning it's fixed, and then we just change the connector widths. Again, the expectation is that if we decrease the connector widths, the band gap should get larger, because then the resonator will resonate more easily. However, again, it's not the case, because for the very thin resonators, so initially it increases, and here we have strongly coupled Bragg resonant gap, for example. But then we have the modes, the modes of the connectors, and then the band gap shrinks. So what I'm trying to show here, that the parameters, they affect the band gap size non-linearly. So even though we expected that with the increase of the resonator, we will increase band gap size, for some configurations, we have extrema. Right, it's also the same for the connector widths. In our paper we plot the maps of this. Right, so I'm not showing them here because it's not that easy to follow, but we've done calculations for all the possible configurations. And then again we decided to check this, the impact of the connector thickness experimentally. And as you can see here, for the thin connector of 0.3 millimeter, we have like very good correlation both for the P and S waves. So if you compare the red and solid black curves, you can see that the thinner connectors, but not too thin, definitely beat the thick connectors. And now, what I'm doing, I'm changing slightly the angle. So I'm rotating a bit more my resonator. So now it's 40, not 30 degrees. And then I take the connector with 0.2 millimeters for what the band gap was 86, which was lower. But now I can see that it's actually like if I rotate the angle, I also can change, I can either increase or decrease my band gap size, and here I'm actually increasing it. So again, to prove you that the band gaps, they non-linearly depend on the connector widths, the angle of rotation, and the resonator size. Then we decided, because we are from aerospace engineering and we want to make our structures lighter, and so these crystals they call single phase, meaning that we have only one solid and air. So either we can make them thinner, right? So we decided to check the transmission loss for the different number of arrays, and we saw that approximately like for the peak frequency we lose like 20 dBs which removal of each layer. But we found that the 3 cells in direction of propagation actually gives us more than like 60 dB attenuation, which are quite good. So the 3 cells is usually enough. Then let's do the following. So let's take the resonator size, fix it, and just rotate it. 5 minutes, okay. And then just rotate it. Here I have 45 degrees, meaning that I have P4MM, a very large resonator, very thin connectors. I have very large band gap of 160%, 116%. And here I have very large imaginary K numbers. Here I cannot even see it. So this means that this is the strongly coupled Bragg resonant band gap, and we will have extremely high attenuation. And this is the P4MM, right? It's not P4GM. Here, this is the P4 because its alpha is the 40 degrees, and still we have the same, basically the same picture, just a slightly bigger band gap. But if I have alpha of 0 degrees, what happens that my resonators will connect, and then they will not actually resonate, meaning that I'm basically killing this local resonant band gap, and I have only Bragg, very small Bragg band gap here. And so this is how it looks, right? So the now resonators are connected, so meaning that if I remove the, so if I forbid my resonators to resonate or to vibrate, then I'm killing this huge band gap. So if you can see here, compare the blue curve for this structure when the resonance is connected with the solid or red curves when they can resonate, you can see significant difference both for the P and S waves. So the local resonator, of course, is crucial here. And then so where do we stand like in the literature, right? Because there are a lot of works on phononic crystals. So in this work we report both experimentally and numerically like extremely large close to 120 bandgap, close to 120% bandgaps. And also, what is important that the opening frequencies are quite low. It's around 40 kilohertz. Because, for example, there are works which report only numerically, not experimentally, the phononic crystals with a larger bandgap, but the lower frequency is higher. And we would like to have the lower frequencies of the opening frequency for the bandgap, because then we can make our structure smaller in order to block the lower frequencies. Usually these are the frequencies that we want to eliminate, especially in aerospace engineering. So there is one work that reports like a bit larger bandgap, and it's quite also it's quite recent. It's 2023, but they report it only numerically, and we actually could not repeat it, because if you look at this structure, so the connectors here, they are pixel size, so they are super thin, and it's simply impossible to fabricate. But also this structure, it has this very intrinsic features. This also has some antennas. So we could not replicate it, because it's done via the optimization procedure, which is one needs to perform it, and we did not have time for that. But we propose a very simple structure, just solid squares, connectors that anyone can repeat and use it in their device or structure for vibration protection if need be. So to sum up, I hope I prove to you that the band gaps in single-phase phononic crystals, they appear due to the Bragg scattering and local resonance mechanism, or their combination. And if we want to achieve higher attenuation and larger band gaps, we must couple them. And the local resonance band gap always beat the Bragg gaps. So the design parameters effect on the band gap side is often nonlinear. And we can achieve extremely large attenuation and band gap size up to 120% for any of the structures having the symmetry group with square Bravais lattice. So not necessarily non-symmetric P4GM, it can be also P4MM or even P4, which just has a lower symmetry. If we position the resonators and pick the proper connector thickness. So symmetry is not like a necessary ingredient, right? So for different symmetry groups, we can still achieve the large band gap. So these are the results in publications. In case if you, the last one is under review in the Journal of Sound and Vibration. So I hope it will go through soon. So this summarizes everything that I've said today. And also, I'm hiring graduate students, so feel free to spread the information. Thank you.